When we think of diamonds, we often picture glittering jewels, symbols of wealth and romance. But to a physicist or an engineer, a diamond is something far more profound. It is a perfect lattice of carbon atoms, locked together in the strongest chemical bonds known in nature. This structure gives diamond a set of extreme properties that make it seem almost magical. It is the hardest known natural material, an exceptional electrical insulator, and yet, paradoxically, one of the best thermal conductors on the planet. 5 times better than copper at dissipating heat. It is also transparent across an incredibly broad spectrum of light, from the ultraviolet to the far infrared. For most of human history, these incredible properties were locked away in rare, expensive stones dug from the earth. But in the 20th century, we learned to forge them ourselves. Using techniques like high pressure, high temperature, HPHT, and chemical vapor deposition or CVD, we can now grow synthetic diamonds in a lab. These are not fakes, they are atomically identical to mined diamonds. We can grow them as large, thin films or as flawless, single crystals, tailoring their properties for specific applications. We have, in essence, domesticated nature's most extreme material, turning a geological curiosity into a high-tech building block. The implications for technology are staggering. In electronics, the ability to rapidly pull heat away from a sensitive microchip is a critical bottleneck. As processors become more powerful, they generate more heat. A material that can act as a heat spreader, like a diamond film placed under a chip, allows that processor to run faster and harder without burning itself out. This is especially crucial for high-power radar systems which generate immense thermal loads. Diamond's ability to conduct heat while insulating against electricity makes it a perfect substrate for the next generation of semiconductors. In the world of optics, a material's ability to transmit light without distortion is paramount. Most materials like glass or sapphire are only transparent to a narrow window of light. But a pure diamond window is a crystal-clear portal for a vast range of wavelengths. This makes it the ideal material for protecting sensitive sensors on the nose of a missile. It can shield a camera or an infrared detector from the searing heat and abrasive forces of high-speed flight, while allowing the crucial light from the target to pass through unimpeded. We are taking the stuff of jewelry and using it to give our fastest machines unbreakable eyes. The United States military, with its focus on maintaining a technological edge, has been quick to recognize the transformative potential of synthetic diamonds. One of the most critical applications is in the heart of its missile radars. Modern active electronically scanned array or AESA radars, like those in the AIM-120 AMRAAM air-to-air missile, rely on thousands of tiny transmit and receive modules. These modules are traditionally made from semiconductors like gallium nitride or GaN. But as the US pushes for radars that are more powerful and operate at higher frequencies to detect stealthy targets, the heat generated becomes a major problem. DARPA, which is the Pentagon's advanced research arm, is funding programs to develop diamond semiconductors as a solution. By using diamond as a substrate for GaN chips, or by creating pure diamond electronics, engineers can dramatically improve thermal management. Raytheon, at its foundry in Massachusetts, is really pioneering this work. The superior thermal conductivity of diamond allows each radar module to be driven at a much higher power, effectively making the radar brighter and increasing its range and resolution. This diamond-enhanced vision gives a missile a better chance of seeing a faint target, like a stealth fighter or a small cruise missile, and provides greater resistance to enemy electronic jamming. It's all about making the missile's eyes sharper and more powerful than the adversaries. Beyond radar, the US is exploring diamonds for something even more revolutionary: navigation without GPS. In a world where adversaries like China can deny access to satellite signals, the ability to navigate autonomously is, honestly, paramount. Researchers at institutions like Lockheed Martin are developing quantum compasses that use a peculiar flaw in a diamond's crystal structure called a nitrogen vacancy, or NV center. This tiny defect acts as a quantum sensor, exquisitely sensitive to magnetic fields. By measuring the Earth's magnetic field with incredible precision, these diamond-based magnetometers could allow a missile, like the Long-Range Anti-Ship Missile or LRA-ZIM, to navigate accurately without needing an external signal, making it immune to GPS jamming. Finally, there is the simple brute force advantage of diamond's hardness and transparency. For missiles that fly through the atmosphere at extreme speeds, especially future hypersonic weapons, the sensor dome on the nose cone faces an inferno of heat and abrasion from air friction. A standard glass or sapphire dome would crack or melt. The US collaborates with companies like Element 6 to produce large, high-purity polycrystalline diamond windows for the seekers of missiles like the Hellfire and the Joint Air-to-Ground Missile, or JAGM. These diamond windows provide a perfectly clear, virtually indestructible shield, ensuring the sensitive optics inside can guide the weapon to its target through the harshest conditions imaginable. China's approach to diamond technology and its military modernization is a story of strategic industrial scale. While it may lag the US in cutting-edge research like quantum sensing, it has built an unrivaled dominance in the production of synthetic diamonds. China produces over 10 billion carats annually, accounting for more than half of the world's lab-grown supply. This immense manufacturing capacity, led by giants like Henan Huanghe Whirlwind Company, gives it a powerful advantage. The ability to integrate diamond-based solutions into its military hardware at scale, ensuring a secure and affordable supply chain that is insulated from foreign pressure. One of China's primary applications for this industrial might is thermal management. Its advanced missile systems, central to its anti-access and area denial, or A2/AD strategy, generate enormous amounts of heat. The powerful guidance electronics and radar systems in missiles like the DF-21D carrier-killer anti-ship ballistic missile and the CM-401 hypersonic missile need to perform flawlessly under extreme thermal stress. China leverages its production prowess to integrate thermal-grade diamond films as heat spreaders in these systems. These films draw heat away from critical components, ensuring they operate reliably throughout the missile's flight and maintain peak performance. Like the US, China is also investing heavily in improving its radar technology. It is actively developing gallium nitride on diamond or GaN on diamond substrates for the AESA radars in its latest missiles, such as the PL-15 long-range air-to-air missile. By mounting the heat-producing GaN chip directly onto a highly conductive diamond substrate, Chinese engineers can build more powerful and efficient radars. This enhancement is crucial for detecting and tracking low-observable US aircraft like the F-22 and F-35, directly challenging America's air superiority. China's ability to mass-produce the necessary diamond substrates gives it a path to equipping its forces with this advanced technology. China also uses its diamond production for optical components, just as the US does. Polycrystalline diamond windows are integrated into the seekers of its electro-optically guided weapons like the CM-802 AKG air-launched anti-ship missile. These diamond windows protect the sensitive cameras and infrared sensors from the harsh maritime environment of salt spray, humidity, and the physical stresses of flight. By ensuring its missiles' eyes remain clear and functional, China enhances the terminal guidance accuracy of its weapons, a critical factor in its strategy to hold naval assets at risk in regions like the South China Sea. China's strategy is less about pioneering new frontiers and more about mastering and scaling proven applications. When we compare the American and Chinese approaches to diamond technology and missile guidance, we see two fundamentally different strategies at play, each reflecting the nation's broader technological and geopolitical posture. The United States is pursuing a strategy of technological overmatch. It focuses its resources on developing revolutionary paradigm-shifting applications that are difficult to replicate. The US leads in the exotic and complex realms of quantum sensing with diamond NV centers and the development of ultra-pure electronics-grade diamond semiconductors. This is a high-risk, high-reward approach aimed at creating a decisive, qualitative advantage that its adversaries cannot easily counter. China, in contrast, pursues a strategy of industrial dominance and rapid application. It leverages its massive state-supported manufacturing base to become the world's leading producer of synthetic diamonds. This gives it a formidable supply chain advantage and the ability to deploy existing diamond technologies, like thermal heat spreaders and optical windows, across its military forces at scale. While its diamond quality for the most advanced applications may lag behind the US, its focus on mass production and integration gives it a quantitative edge. China's approach is more pragmatic and incremental, aimed at systematically improving the performance of its entire missile arsenal. This strategic divide is clearly visible in their supply chains. The United States, despite its research leadership, faces a significant vulnerability. It relies heavily on imports for the raw diamond substrates needed for its advanced research and manufacturing. With China producing 56% of the world's lab-grown diamonds and controlling exports of other critical minerals like gallium, the U.S. defense supply chain is exposed to potential disruption. This has prompted initiatives like DARPA's to onshore production, but overcoming China's cost and scale advantages is a monumental challenge. The U.S. holds the more advanced recipe, but China owns most of the ingredients. Ultimately, the race is between American innovation and Chinese industrial power. The U.S. bets that its breakthroughs in quantum navigation and diamond electronics will create game-changing capabilities that redefine missile warfare. China bets that its ability to rapidly and affordably enhance thousands of its missiles with proven diamond technologies will give it a more immediate and tangible military advantage. It's a classic confrontation, the finely crafted rapier versus the mass-produced broadsword. The outcome of this competition could very well determine the technological balance of power for decades to come. For decades, the most precise way to navigate our world has been by listening to faint whispers from space. GPS has been a revolutionary force, but its reliance on these fragile signals is a glaring weakness in a military context. What if a missile could navigate with the precision of GPS, but without ever needing to listen to an outside signal? This is the promise of quantum navigation, a technology that sounds like it was lifted from science fiction. And at its heart lies a tiny, deliberate flaw in the otherwise perfect crystal lattice of a diamond. This is the nitrogen vacancy, or NV center. An NV center is created when two adjacent carbon atoms in a diamond's grid are replaced by a single nitrogen atom and an empty space, a vacancy. This tiny imperfection traps an electron, and the quantum property of this electron, its spin, is extraordinarily sensitive to its local environment, especially magnetic fields. Using lasers and microwaves, scientists can manipulate and read this electron's spin. Because the diamond lattice holds the NV center in a perfectly rigid, isolated state, it becomes a near-perfect quantum sensor, capable of detecting minute variations in magnetic fields with a precision that classical sensors can only dream of. This is the principle behind the quantum compass. The Earth itself has a magnetic field, a complex and dynamic map of magnetic forces that varies from place to place. While a traditional compass can tell you which way is north, a quantum magnetometer based on diamond NV centers can measure the absolute strength and vector of the local magnetic field with exquisite detail. By comparing these live readings to a preloaded high-fidelity map of the Earth's magnetic field, a missile could determine its precise location. It would be navigating by feeling the invisible magnetic landscape of the planet itself. The strategic implications are profound. A missile equipped with a quantum compass would be completely immune to GPS jamming. It would be on a silent, undetectable navigation path, guided by the fundamental forces of the planet. The United States, through research at Lockheed Martin and various university labs, is currently leading the world in this field. While the technology is still in development, challenges remain in miniaturizing the required lasers and electronics and creating sufficiently detailed magnetic maps. It represents a potential leap in guidance technology. It is a quest to give missiles a sixth sense, an unjammable link to the world around them. We are entering a new era of warfare defined by unimaginable speed. Hypersonic missiles, which travel at more than 5 times the speed of sound, Mach 5, represent a monumental challenge to existing defense systems. Their combination of extreme velocity and maneuverability makes them incredibly difficult to track and intercept. But building a machine that can withstand these speeds is a Herculean task. As a hypersonic vehicle streaks through the atmosphere, the friction with air molecules generates temperatures hot enough to melt steel. This creates a searing plasma sheath around the missile that can blind its sensors and fry its electronics. This is where the extreme properties of diamond become not just advantageous but absolutely essential. For a hypersonic missile to see its target during its final approach, it needs a sensor window on its nose that can survive this infernal environment. No ordinary material will do. Glass would shatter, sapphire would degrade, but a window made of pure synthetic diamond can withstand the thermal shock and abrasive forces. Its unparalleled hardness resists the scouring effect of high-velocity air particles, and its exceptional thermal conductivity rapidly dissipates heat away from the window's surface, preventing it from overheating and going blind. Diamond is the only material that can provide a clear, durable eye in the center of the hypersonic storm. The challenge extends beyond the optical window to the electronics inside. The high-power processors and radar components needed for guidance and communication must operate reliably within this cauldron of heat. Traditional cooling methods are insufficient. Here again, Diamond offers a solution. Diamond heat spreaders can be bonded directly to the most critical microchips, pulling destructive heat away far more efficiently than copper or any other material. This allows the missile's brain to keep thinking clearly, processing targeting data, and making course corrections, even as its exterior is subjected to hellish conditions. Both the United States and China are locked in a race to master hypersonic technology, and both recognize that advanced materials like diamond are a key enabling technology. For these next-generation weapons, diamond is not merely an enhancement, it is a prerequisite for success. The ability to manufacture large, flawless diamond components capable of withstanding the hypersonic environment will be a critical factor determining which nation leads in this new domain of warfare. As we push the boundaries of speed, we are finding that we must rely on nature's most resilient material to survive the journey. Our journey has taken us from the fundamental challenge of hitting a target to the quantum realm and the hypersonic frontier. Along the way, one extraordinary material has appeared again and again, the synthetic diamond. It is clear that this perfect lattice of carbon atoms is no longer just a luxury item, it has become a critical strategic material, a cornerstone of next-generation military technology. The race for missile superiority between the United States and China is increasingly becoming a race for diamond superiority, a competition in both groundbreaking innovation and industrial-scale production. The ongoing trends point to a future where diamond's role will only expand. As stealth technology advances, radars will need to become ever more powerful and operate at higher frequencies to find their targets. This will drive an even greater need for diamond electronics to manage the immense heat generated. As cyber warfare and electronic jamming become more sophisticated, the ability to navigate without GPS will shift from a desirable capability to an absolute necessity, pushing the development of diamond-based quantum compasses from the lab into operational systems. Diamond is the key that unlocks performance in these contested environments. The strategic competition will intensify around the diamond supply chain. The U.S. faces the critical challenge of securing a domestic source of high-purity diamond substrates to fuel its innovation and insulate its defense industrial base from Chinese leverage. China, meanwhile, will work to close the technological gap in quality, aiming to translate its dominance in production volume into a dominance in high-end applications as well. The global balance of power could be influenced by which nation can more effectively master the entire life cycle of this critical material, from crystal growth to systems integration. In the grand cosmic dance of precision, where victory is measured in millimeters and microseconds, the quest for the perfect material is relentless. For now, and for the foreseeable future, that material is diamond. It offers harder windows, cooler electronics, and smarter sensors. It provides an unbreakable edge, enabling missiles to fly faster, see farther, and think more clearly under the most extreme pressures imaginable. The glittering gemstone that once symbolized enduring love has been reimagined as a symbol of enduring power, forever changing the face of modern warfare. Please don't forget to subscribe to Gemstone Academy for more deep dives into the world of gems and jewelry.